Alright, so just a quick lesson on position time graphs before we move into velocity. Position time graph is just another way to represent motion. We've looked at motion diagrams. This is just a way that's convenient in most other scenarios. A motion can be presented on a position time graph, and that way you can use a best fit line to represent where the object likely is located at any specific point in time. It's the best fit line is not necessarily going to be exactly what your data looks like, but it does give us a very good estimate. Now what we can do with this particular motion graph is estimate when the object has reached 50 centimeters beyond the origin. Now we know that the origin is right here, so 50 centimeters beyond that point would be roughly halfway between the 40 and the 60. If we trace that over, we can figure out that the position of the object was about here. We trace that down somewhere between the 0.2 and 0.3 seconds, roughly 0.25 seconds. We can also estimate where the object is at a certain time. So at about 0.37 seconds, be somewhere in this region, we can trace that up to where that lies on the best fit line, about right here, and we find that that corresponds roughly to maybe 68 centimeters, somewhere between 60 and 80 centimeters. Now we can also infer how the motion of the object occurs based on the motion, the position time graph. For instance, just see if you can describe the motion of the car shown by this graph real quick. Hopefully you realize that the car starts about 125 meters away from our origin point and actually comes toward the origin. After 5 seconds, it actually passes the origin and continues to move in that same direction past the origin. Now, assuming that positive is in east and negative is the western direction, when was the car 25 meters east of the origin? We can estimate 25 centimeters to be about right here. Trace it over. Corresponds to this point on the best fit line. Trace it down. So roughly 3.4 seconds. Or rather 3.9 seconds. Another example we can look at, if we have two best fit lines for two sets of data on the same position time graph, we can actually figure out where those two objects meet. In this case, we have runner A and runner B. Where do you think runner A will pass, runner B will pass runner A? Well, it's going to occur where the two lines cross. In other words, they pass each other where their position is the same. Obviously, when they're passing each other, their time is also going to be the same. So let's just picture another runner here. We'll call it runner C. Based on runner C position time points, do you think runner C will ever pass runner A? Probably not, because these lines are always going to get further and further apart. Unless one of them changes something about how they're running, runner C will probably never catch up to runner A. Finally, let's look at this question. When runner A was at 0 meters, where was runner B? Hopefully you answered that runner B was at negative 50 meters from the origin. In other words, 50 meters behind the origin. Because when we look at the point in time where runner A was at 0 meters, we see that it was 0 seconds. When runner A is at 0 meters, runner B is at negative 50 at 0 seconds in time. In other words, we're looking for the point where they share the same time value. Finally, the last question. See if you can create a position time graph of this motion diagram of a baby crawling. You want to pause this video because I'm going to draw it here real quick. Okay. So we always want to put our position on the, I'm sorry, we want to put our time on the x-axis, measured in seconds. By the way, I should have told you that the time between each interval of this baby crawling is 1 second, but it wouldn't really have mattered because the shape of the graph would still be the same no matter how long those intervals were. Position will go on our y-axis since that is our dependent variable changing with time. Put 0, 0 here at 1 second. Position is 20 centimeters. At 2 seconds, the position is 40. At 3 seconds, the position is 60. And usually 3 lines is enough to make a linear relationship here. We can kind of just extend that out and know that this linear diagram is similar to a motion diagram with evenly spaced intervals. If these intervals were not evenly spaced, it would be a much different story, but that's what we'll get to in later sections when we talk about acceleration. Thank you very much, and we will talk about velocity in the next section.